Hello everyone. Today we're going to start a new chapter, chapter 14, which is kinetics of particle, work, and energy. In this chapter 14, today we're going to cover the work of a force. So if you apply a force, for example, in the picture, if the man apply force on the pedal and then the bicycle moves in a distance. So how much work is being done? We're gonna see that. So today's learning objective is define work of a force. So how work is being, we can define a work and then how we calculate them, and we're gonna see that for different scenario. So formulate work for different type of force. So if we apply different type of force, how we can calculate for work for that force. So for example, in this image you see this man is pulling and pushing cart at the same time. So and if the cart moves by a distance, and so there's some work being done and we can calculate that. Second, you see these paratroopers is falling due to their weight and gravitational pull by the earth. So there is also some work of their weight. So we're gonna calculate, formulate equation for that too. And finally, in the image you see there's a spring. So if we compress or pull that system, the spring is going to be extended or compressed. So there will be some work done on spring. So we're gonna see that too. So now let's start with what is work. Work of a force. So if we apply force onto a particle and it undergoes a displacement in the direction of the force being applied, then we can say some work is being done. So so there has to be a force, and then there has to be a movement or displacement along the direction of force. Then we can call it a work. So let's see an example. If this is a path of a particle and we have the particle here, its radius of curvature was here r, and then now after movement it is r prime. So the distance is traveled is dr. So these are all vectors. So if we say this dr, this distance, its magnitude is ds, right? And there is a force applied any direction which makes a theta angle with the direction of the movement of the particle. Then we can say that the work can be defined as du equals to f dot product with dr. Now du, you see I didn't put a vector, so this is a scalar. So work is a scalar amount. So when we say dot product, just to remind you, so dot product of two vector, if there is a vector a and there is a vector b, and there's angle between them is theta, so dot product of two vector is defined as ab cos theta. So same if we apply that concept here. So here we will have f magnitude, so these are not vectors, so f dr, magnitude of dr is ds, and cos theta. So the angle between them is theta here. So f ds cos theta. One thing to remember, that if there is no displacement, so if ds, the displacement is 0, so there is no work done. For example, if I push a wall against the wall, if I push, or many of us push against the wall, and if the wall doesn't move, so no work is being done, so work is 0. So now let's see a little more deep into this equation. So if we see f, so if we write in this way, is f, so f in this direction of force, right, force. So if we do f cos theta, so this is the component of the force. So if we write f cos theta, it's just rewriting multiplied by ds. So what it means is that f cos theta is the component of force along the direction of displacement ds. These are all scalar, so magnitude of f cos theta and ds, these are all scalar. So now let's see more about this equation theta. So what if theta has a different value? So when theta, so let's say different scenario, when theta is equals to 90, then cos theta equals to 0. So if, so one scenario one, if the angle theta is between the if the theta between the force and then the displacement between dr and force is 90 degree, then the work is 0, so there is no work being done. This is one scenario. What if theta is greater than 0, theta is greater than or equals to 0, and less than or equals to well, not equals to, because equals to will be 0, less than 90, then we will have some work. Then du will be positive, because the cos theta, the force component will, the f cos theta, the component will be positive, and we will have some positive work, so they will be positive. The third scenario, if our angle is greater than 90 degree, and less than or equals to 180 degree, then we will have opposite direction, because the component will in the picture, if you look at the picture, the component, if it's more than 90 degrees, so the component will be in this direction, so it's opposite, so the force direction is opposite to the movement dr. So if it's opposite direction, then we will have our energy, the work is negative. So this is just some things to remember. If the theta, the angle between the work and the displacement, is less than 90, positive work. If greater than 90, which is the direction of the displacement and force is opposite, then you have negative work. And if it's 0, if it's the angle between 90 degree, then there is no work. So so let's see how this equation that we derived, du equals to f cos theta, can be applied for different work conditions. So Um, First, let's see what would be the work for of a variable force. So instead of constant force F, what if the force is variable, changing? So it's easy. If your force is changing, what do? We do integration. So if there's a variable force, for example, the component F cos theta is changing with respect to when it's moving its direction. So this one is the initial position, and then the F cos theta is changing up to a new position S2, and we can always do an integration to find the work being done. So the work done from point 1 to point 2 can be done with integration of that equation that we derived, well, we defined in previous slide, F cos theta ds. It's the same equation, and the equation, it will be integrated on the axis of S from S1 to S2. So these are all scalar. So this is our second equation. When if we have a variable of force, then we're going to use this equation. What if this force is not variable? What if the force is constant, which is moving along a straight line instead of a curved line? So let's see. Constant force moving along a straight line. So if there is a movement, the initial position is S1, and then the final position is S2, and then the force is constant in that direction, and it's making an theta angle with the direction of movement. So if F is constant, the scenario is F cos theta is a straight line. So in this picture, you see F cos theta is changing in this curved direction, but here F cos theta is a straight line from S1 to S2. So how this scenario can be calculated using the equation that we have just derived. So in this case, we will have u1 to the integration. This equation will become, since f is constant, f cos theta is constant, so it will be out. We can take that out of the integration. We'll still have the integration from S1 to S2 on ds. So, and if we take integration of ds, it's just s, so which will give you f cos theta s2 minus s1, because integration of ds is just s, so we can call it delta s, which is s2 minus s1. So this is the special case scenario. So if the force is variable, we have to use this equation. If the force is constant, like so, then we're going to use this equation. So now let's move to another different force scenario, which is work of a weight. So you saw the image that I showed you at the beginning, where I was talking about the examples. They're man free falling, the paratroopers free falling due to their weight and gravitational pull. So if there's just free falling, there's no other force acting, how can we simplify our work equation? So we'll go back to our dot product concept. So if we have we defined work as a work from point 1 to point 2 is a dot product that we defined between force and distance. So in this case, when some object, so any particle, let's draw something, will be easier. So if we have in 3 dimension, right, x, y, and z, there is a particle in 3 dimension is free falling, no other force is acting, only force is acting is its weight pulling it down. So only force is acting is w, and then maybe it's moving another direction. Let me choose a different color. So this is the path of the particle, but only force is acting is its weight downward. So then the work done can be calculated using F dot dr. So the force only acting is downward, so what's the dot product? W negative, so downward in j direction, is dot product with the displacement. So if the particle previously was here and now here, so it's moving, the previous coordinate was r1 vector, and now the position is r2 vector. Let me simplify this. R1 vector. So the change in position, which is here dr. So if we say dr vector is dx in I direction plus dy in j direction plus dz in z direction. So we will have multiplication between dxi plus dyj and dz in z direction. So when we do dot product of vector A dot product with vector B, the so it's ax bx plus ay by plus az into bz direction. So since we have only j, so only this one and this one will be valid. Since the force doesn't have an I and z component, those will be 0. So we'll be down to negative w and dy, and rest of them will be 0. So if we have variable force, then the work done will be y2 from y1 to y2, and integration of w, their weight, and dy. So again, if we take the integration of dy, we'll just be left with y2 minus y1 So minus w y2 minus y1 after integration. So it will be only minus w delta y. So work of a weight can be found is using only this equation, which is negative w delta y. So why the questions comes why the work is being negative? Because the particle is moving here. If you see the particle is moving kind of upward, and the force is working downward. So if the work the displacement and work direction are opposite, then we will have negative work. If the particle, if we say different scenario, if the particle is moving downward, so if the particle is moving this direction, just moving downward, and then only forces acting is their weight, then the work will be positive. So this is the work of weights. Now let's move to the another last concept for today's lecture, work of a spring force. So work of a spring force. So if we pull or push a spring, you know there is a resistance to the displacement. So that's the work of the spring. So let's draw a spring attached to a wall. We have a spring. So we're pulling the spring. So there's a particle. We're pulling the spring to extend, for example, amount ds. So the spring being elongated, but the force the spring is applying is against the displacement. So there is a force opposite to the displacement. So we're moving the spring in this direction, and the force inside the spring is to retain its original position, original shape. So there's a pulling force opposite to the direction of movement. That's why we can call it F, that tends to keep the spring in its original position against the extension. So this is the original position, and we are moving this direction ds. So we'll call force is opposite to the displacement of the spring. So it is a negative force. So what will happen is that the work done will be if this position is S1 to S2, S1 to S2, so we'll have S1 to S2. The work F ds will be, we know for a spring the force is spring constant, and then the distance s. So the equation becomes ks ds. So s is the current position of the particle, distance s. So the equation, and it will be negative because, like we discussed, the force is acting against the direction of the displacement. So if we take integration, we will get negative half k s2 whole square minus half k s1 whole square So that will be our work of a spring. Negative half, we can take the k and s out of the equation. So s2 whole square minus s1 whole square. So this is the work of a spring force. So in next classes, we're going to use this equation to solve problems of different force scenario, where how do we apply this equation to find the work of a spring. So till then, see you. Thank you. See you in next class.